morning, good morning, good morning. Mr. G here with the weather forecast for your February 21st, 2022. Today is Monday, it's President's Day. In my previous video, we talked about the medium range 2-week forecast. In this video, we are going to deal with the severe weather threat that's going on across the nation. So let's jump right into it. This is going to be our severe weather outlook and what we're going to deal with thunderstorms, especially across the southeast and in the southern plains and on maybe into the Great Lakes in Ohio Valley. Could the Great Lakes see some thunderstorm activity? We'll talk about it right next, okay? So let's take a look at some of our charts that we got going on here. And this is going to be our winter. Oh, no, that's the wrong one. That's for the next video. Severe weather. Let's take a look at. This is the one I'm looking for. Here's our severe risk analysis. And all right, I am sitting in front of the analysis thing here. Let me move my head. So let's move on out the way. So, well, anyway, you see it right there. Okay. I shouldn't be sitting right here. But anyway, so this is the, you see the area of severe weather going on there on that map there, that little baby map. You see that severe weather? And that yellow is a slight risk of severe weather, and the darker green is a marginal risk, and the light green is a general thunderstorms. That means they are just garden variety, regular thunderstorms, no severe weather expected from that, but you do see that area where that yellow is, and that is for your severe risk for thunderstorms. All right, so the SBC outlook does have a tornado threat. Is low, a very low. It's about a 5% or less threat for a tornado or two. And then the severe thunderstorm risk is high, as many of the parameters for severe thunderstorms and damaging winds is kind of high, moderate high. I would say moderate to high. But I'm going to give it a high because I think we'll see a bit of severe thunderstorms, but I don't think we'll see much tornadoes. Maybe one or two tornadoes is possible. I would be prepared and on the lookout for that risk for a tornado or two. All right, hail is also a possibility, especially anytime you have the risk for tornadoes. You can see some hail in the vicinity of the tornado. So as far as our severe threats, the tornado threat is slight. There's also a slight chance for damaging winds. That's about 15%. And the large hail percent is about 15% as well. And flooding is slight. We'll give it a 15% as well. And the flooding is mostly because of some of the thunderstorms are going to be affecting areas where we saw a lot of heavy snow, and that snow is melting, as well as the rainfall from the thunderstorms is going to overwhelm some of the rivers. So you can see some river flooding and some small areas of flooding. The National Weather Service have several products posted right now about the potential for flooding, especially in many locations across the Ohio Valley and the mid-Mississippi Valley, where you often see a lot of flooding after the snow starts to melt and things like that. So we do have that in place. So let's jump into our severe weather GFS analysis, and we're gonna go through several parameters here, and I'm gonna talk to you about several different things that we look for as far as severe weather. And the first thing we are going to look at is our CAPE, and our CAPE is convective available potential energy. And I've heard some folks call this tornado juice or thunderstorm. I would call it thunderstorm juice more than I would call it tornado juice. But this is what you need if you want to see thunderstorms. At least then, one of the first things we look at. It's not the only thing to look at, because you get a lot of CAPE and nothing happens. And I've seen that many times where you have a lot of CAPE and you don't get squat. I'm like, what's going on here, man? It's humid. It's hot. Where's the thunderstorms? And And you be like, oh yeah, but there are some other things. We're going to talk about that. We are going to talk about that. All right. Just hold on to your horses. Hold on. It's coming. So anyway, let's look at our cape. And this is a 3-kilometer knob, okay? Because it goes out about 60 hours. And this is about the time. This goes out to about Wednesday. So we're going to that's about how much time we're going to be dealing with this particular storm, and we are focusing on the southeast. So let's move this here, and we're going to look at how this progressive. And I really want to show you something cool that's on this map. And you can see our cape comes up, and you can see right now the cape is about, at some instances, hit about 2,400 joules. It does hit about 2,000 joules in a few locations. So that would probably be our best bet for the areas that are seeing that we'll see some severe thunderstorms develop. But we'll see thunderstorms develop throughout this area. And this is what it's going to look like for today. So this is what we expect today. And you see that cape here, and there could be some thunderstorms in Dallas, Fort Worth, across into maybe Shreveport, Louisiana, Baton Rouge, and maybe parts of southern Pine City, Arkansas, as well as into Jackson, Mississippi. If you're in, and you could also possibly see thunderstorms into Alabama as well. So let's move that on along, and we'll see how that kind of runs for us. And you can see that progress and makes its way across. And you see some of that cape lift all the way up into the Michigan, into the Great Lakes. So this is why we think that could possibly be thunderstorms in the you could possibly see thunderstorms in the Ohio Valley. You could see some rumbles of thunder, but I don't expect anything severe to get to those regions, partly because it's not warm enough really, and there's not enough energy available for that, for those types of storms, and you don't quite have the bulk shearing needed as well. So I think just general thunderstorms, maybe some light thunderstorms, nothing too severe. Maybe it's just enough lift and instability to get a few rumbles a rumble of thunder or two. So I wouldn't expect too much in the way of severe weather or thunderstorms if you're in the Great Lakes area. But don't be surprised to hear a rumble of thunder. So that is a look at what our cape looks like. Now we're going to go into our next thing that we expect and that we look for when we have situations of severe weather. And let's make our map so that everybody can see. And this is our mixed layer. Okay, so when you talk about sin, what is sin? It's not sin when you don't pay attention to God or don't follow the Bible. That is CIN, not SIN. Now, CIN is the convective inhibition in the atmosphere. So it's the thing that suppresses convection. And when you have this tells you that this is what the atmosphere needs to get baked. This is the cap. When you hear us meteorologists talk about a cap in the atmosphere, it's kind of a lid. And what that means is that the atmosphere has to exude this much energy to break through it to initiate thunderstorm development. So it has to break through that cap. And what this parameter shows is that the atmosphere needs to exude 100. You see how it changes as it goes up. This is how much energy is needed to break through that cap to initiate thunderstorm development. So that's what that looks like. So there's a lot of cap in place, and that's one of the reasons why I don't expect a severe weather outbreak to occur, because the cap is kind of strong, and the storms really would have to kind of do a lot to get through the cap. But the cap is not equal everywhere. Some areas have stronger cap than other locations that's going to be in this parameter for thunderstorms. So that one of the things that contributes to how severe a storm is the work it put in to break through the cap. And a lot of times, once it breaks through the cap, it's like opening the floodgates. And that moisture, that unstable air could rush right in, and those thunderstorm heights really start to build. When you have a strong cap, a lot of times that adds to the severity of the thunderstorm is the action of breaking through that cap. And sometimes once they break through, it's kind of like opening the floodgates to a dam. And once that water starts coming through and you really see it starts coming, this is how those thunderstorm updrafts get when they break through that cap finally. So, and then you often see that when you have instances of elevated thunderstorms where the storms are a bit higher up in the atmosphere, where the cloud bases are higher. You don't really see that as a problem. Well, sometimes I think you can see it with tornadic thunderstorms with low cloud bases, but you can also but the cap sometimes can be much lower when you're dealing with those kind of thunderstorms. But a lot of times we see it with the elevated thunderstorms. Nose is getting kind of stuffy. So anyway, let's take a look at our next parameter. And this is our relative helicity. Now, the relative helicity is when what we see when the atmosphere, say as the air rises, right? It spins. This looks at the rotation in the atmosphere, the overall rotation in a rising thermal. So as that air rises, it spins. This is your mesoscale. This is when you look to see what is going on for your mesoscales. This is mesoscale meteorology here in those helicities. And as you can see with these storm systems, especially right in here, as you can see, there is not a lot of vorticity going on with these systems. This is why that tornado threat is at a 1 out of 5 right now. Why there's a 5% or less chance that we'll see a tornado, because you're not having that shearing. You're not seeing that rotation You're not seeing that rotation so much in those thunderstorms. I think a lot of these thunders with this pattern, how you see how it's, I'm hitting the microphone, how it's lined up. See, this here indicates linear thunderstorms. Linear thunderstorms. A linear is a squall line. You see those shelf clouds, long linear shelf clouds. As the thunderstorm progresses across the valley, you see those that line of clouds that kind of stick out in front of the storm. I think we'll see those kind of storms, not so much as discrete supercells, which the ones we're going to see when you see an organized tornado outbreak. Because with supercells, what creates those conditions is when you have a thunderstorm, right? You get a thunderstorm, and that thunderstorm dissipates. When that storm dissipates, the air comes down. You have the downdrafts. And when that downdraft air hits the surface, it spreads out. And when it spreads out, it creates boundaries, surface boundaries. They're like little mini cold fronts, because that cold air came from up high aloft and sank to the surface. And when it sinks to the surface, that air is warmer at the surface. So it spreads out and lifts the air around it. So it can create new thunderstorms. And it kind of be a self-propagating thing, because those thunderstorms feed off of the boundaries from decayed thunderstorms. So that's what you see when you look at those, when you deal with discrete thunderstorm cells. Supercells do that a lot. They do that a lot. They create boundaries, and those new thunderstorms form in the boundary outflow. The outflow boundary. That's the word I'm looking for. Outflow. From the bases of those storms, when they collapse, they create new storms. So, and this is what this looks at. This helicity deals with that. So let's take a look at the next thing we're going to look at here. And this is our bulk shear. This is the bulk shear, and we want to look for what's going on. When we look at the bulk shear, this is our wind speed changing with direction, with altitude. So as it goes up, air flows in, but it rotates or it changes direction. We want to see this direction. See how these are? You want to see this direction this way, and then you have winds blowing this way at a different. So you have winds at one altitude going this way, winds at another altitude going this way, and it creates a rotation. It creates a spin because they cross each other. That's called shearing. And a lot of storms don't like to be sheared. Hurricanes especially, they don't like shear. Shear tears them apart. They can't organize if there's a lot of shear. But severe thunderstorms, on the other hand, love shear. They thrive on shear. The shearing really gets your thunderstorm. They really kind of like that. And they really like to be sheared, the shearing that takes place. That's how you get your severe thunderstorms. If there's a lot of shear, they change it with height, creates those rotations, those eddies that form tornadoes. So if you take your shear, you got your wind with height, then you have your column there. They usually rotate horizontally, but they hit that. But then those updrafts hit it. You hit the updraft, your downdraft, going like this, and that column of air that's spinning horizontally because of the shear turns upright. And once it turns upright, then it tightens, and then that's how you get your funnels and your tornadoes to form. So that's why we look at shear when we're dealing with severe weather. So let's take a look at the next map. And the next one is going to be our LCL. And our surface-based LCL is our the lifted, our ability for the atmosphere to lift, the buoyancy of the atmosphere. And as we look at it, as we run it, as you can see right here is where we've been dealing with that severe weather. And this is where we're seeing the best LCL here. Now it makes its way across. But anyway, this deals with the lift of the atmosphere. And now here's our lifted index, and this is a combination of several parameters, and this will show us our ability for the atmosphere, how much air parcel to rise. And another thing to mention about LCL is the LCL, if you take a column of air, say the temperature is a certain temperature at a certain height, right? And if you take another air parcel and rise it to that same level, that differences in that temperature in this parcel that you rose to this level as compared to the parcel that was already there, that temperature is your instability. So say it was 10 degrees at this level, and you took another parcel and you rose it from the surface and you lifted it up to that same level, and then it was 7 degrees. Well, that 3-degree difference is your instability. It's the instability in the atmosphere. That's what the LCL stands for. It's early in the morning, and sometimes my brain ain't clicking all the way. So anyway, but you can see the lifted index here as those thunderstorms start to take shape. And you can see those parameters that these thunderstorms. What is really cool is that you can see the frontal boundary. You can see the front, how it makes that really beautiful cutoff line, that beautiful line. That's where our front is passing through, and it's pushing all that moisture and all that energy to the south. It's suppressing it towards the south. As you can see that right there, that's really cool. I thought when I was looking at these maps, I thought that was really cool to see how well defined that was. Now this is our lapse rate. This is our temperature. And again, another look at the instability in the atmosphere. This is our hail index right here. When you get those lapse rates, and the higher the lapse rate, that's the altitude of the heights of the storms. And you see that hail. This is what we look at when we want to determine, if a storm system is going to be a hail producer. So we look at those lapse rates. This is those updrafts, how strong those updrafts are. Are the updrafts strong enough where when you get that rain start to fall and it falls into that updraft, can the updraft lift it up again? So the stronger those lapse rate, the stronger those updrafts are. And it picks those rain droplets up and twirls it around. It makes it round through the storm system, but as it does, it's a ball of ice. You know, all precipitation falls frozen first, and it melts as it falls into the warmer air as it gets closer to the ground, and it comes down in rain. But if that rain did not melt into rain, it would be snow or ice. So you would see that fall out of the clouds. But those updrafts keep lifting those little balls of ice, and they grow and grow and grow and grow until they become so heavy that those storms can't hold on to them anymore and they fall. Then you got hail. That's how you get hail. It's when you get those steep updrafts that keep the really strong updrafts that can keep those ice balls, those water droplets, those frozen water droplets, and as they rise, they collect other water droplets. They kind of accrete together. There's an accretion process that takes place in the turbulent nature of a thunderstorm. Remember, thunderstorms are up and down motions, up and down, up and down. That's what makes your thunderstorm. It's the same thing that produces lightning, up and down, up and down. So when air molecules are colliding into each other, they're going up, some are going down, they're colliding into each other, boom, 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 boom. They are creating an electrical charge as they exchange electrons. They bounce the electrons off because they're collisions, bam, 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 and those electrons are flying everywhere. And they're falling to the surface. They're falling on top of buildings. They're falling on the trees. They're going through the clouds. They're going everywhere. So it's creating electrical charges. And when those charges neutralize, they discharge. Boom, you get your lightning. And then boom, you get your thunder. That's how thunderstorms are created. It's because thunderstorms are very violent. The atmosphere is going through a very turbulent period because there is this creating a lot of friction. That updraft, downdraft, this is why you have a lightning core. The lightning don't just randomly occur throughout the storm. The lightning has an origination point, and it's usually that line where that updraft and that cold air. Now you can see lightning everywhere. That's because those electrons are knocked all over the place, and they have to neutralize. They have to say, hey man, I know you. You part of my crew. And they reconnect together again. So you get that lightning and thunder. So this is what you look for when you want to see that. We want to see those lapse rates when we're looking at thunderstorms like that. So that is a look at the severe weather threat for right now. As you can see that that severe weather is going to be there across the southeast. It may spread some thunderstorms up into the Great Lakes region as well as the Ohio Valley. Could see a thunderstorm or two, but that severe weather is going to be confined to the far south, into Arkansas, Tennessee, Mississippi, Alabama. I don't think you'll see weather right along the immediate Gulf Coast. I don't think you'll see any severe weather in New Orleans, Biloxi, Mississippi, Mobile, Alabama. I think you'll be out of the range. Here's another advertising. Hey, I think this one is what we're selling. Now we're selling looks like a mattress or something. So anyway, thanks for watching this video. And this is a severe weather video. This is taking a look at the severe weather forecast for the next couple of days, dealing with that stuff across the southeast as we have that severe storm threat in Louisiana and Arkansas and Mississippi, Alabama, as well as Tennessee. Thanks for watching this video. Do you like thunderstorms? Do you like do you enjoy thunderstorms, or are you afraid of thunderstorms and you hide under the bed when you have thunderstorms? Do you have pets that are afraid of thunderstorms? Leave your comments in the comment section. Leave a like. Please share the channel with your friends and also subscribe. All right, I'll see you in the next video. Have a good day. Thank you.